Hey everyone. So we're going to get started here pretty soon. So the link for the problems that we're going to do is in the video description, along with any other way that you want to support the channel, either through liking and subscribing. There are many ways to that's highly recommended, but we have other links like Facebook, Twitter, Patreon, PayPal, a bunch of ways that you can support the channel. But if you want to solve the problems at the same time that we're going to be solving them today, the link is in the video description. So the way that we're going to do this today is I'm planning on doing 300 problems. This page has, I don't know how many does it have? How many does it have? It has 435, it looks like. So what I want to do is I want to do 300 of them because that's effectively what we did yesterday. But we could end up doing fewer because algorithms problems take a little longer to solve in some cases, but we'll see. So if we end up doing fewer, I want to do at most a 7-hour session. So I don't want to go beyond 7 hours because that was like the limit yesterday. 7 hours total. So the way that we're gonna do this here is we're gonna do 100 problems, and then we'll take a short break. Then do another 100 problems, take a short break, and then maybe do another 100. We'll see how much time we have. Ready to learn? Ready to learn indeed. Awesome. Hi, thanks for the sessions. You're absolutely welcome. So we'll get started right on the hour. And for this one, because we have not done algorithms problems before, we're just going to start from the top and work our way down. Start with question 1, 2, 3, and just go all the way down. And if you want to have anyone else join, please share this the video link up above with everyone that you know, and that'd be really good. All right, so I shared the live stream on the Discord server is also in the video description, and I shared the link with them. Best resource for algorithms. Is that me or the page? Yeah. Let me turn off my audio, the speaker audio, so that notifications don't mess the live stream up. I also have my iPad here in case we need to do some calculations. And it looks like for the first problem here that there are going to be some calculations. Okay, so, oh, maybe there's a delay. Let's see, is there a delay? Okay, yeah. Okay, yeah, it's just a delay. Suggest some book sources for algorithms. So, I mean, CLRS, which is Introduction to Algorithms, the CLRS, if you don't know, is the authors of the textbook, the last names. So that's pretty much the only one that I can really recommend, other than algorithm designed by, I forget the authors. So algorithm designed by, let me look up. Oh, Kleinberg and Tardish. Yeah, so those two textbooks are the ones I've used in various classes and whatnot. So you're going to teach all course subjects? Eventually I will. I can only do so much. But okay. Bible of algorithms. Yes, thank you. I appreciate it. So the way that this works, for those of you who are just joining us, um, so we're gonna visit a question, and you just put into the chat what you think the answer is, and then we'll talk about it. Opinion on Man-Burr book. I have no idea what that is. Never heard of it. Let's see, Man-Burr. Oh, I've never heard this book. Introduction to Algorithms, a Creative Approach by Udi Man-Burr. Never heard of it. Don't know the person, never heard of the book. So I can't give an honest opinion. Okay. Explain how Huffman coding works. The thing is, that's my least good subject, but I know how to do them. I know how to do them. I don't know like all the guarantees on the runtime, not runtime, but like the size and everything of the words that in the representation. Yeah, but I know how to solve the problems. It's just I don't. This is the one thing that I just don't know because I was never taught it. And I see, of course, the very first problem is Huffman coding. So, what can you do? Yeah, the idea is that you are, instead of just giving a string of a certain size associated with each character to translate it into binary to transmit as message, what you do is you try to give fewer occurring characters a longer word if possible, and shorter characters, characters that occur more often with a shorter string. Which makes sense. If they occur more often, we should have the string be shorter, and the longer ones go to the letters that occur less frequently. That's the basic idea. I don't know all of the proofs and everything behind that. I wish I could draw it directly on the screen, but I can't. I can't even click here. If you, yeah, you can't see my cursor, but I can't actually click anywhere except for where the answers are. So let's see. Let's move this here. Where are you from? United States, Prashant. I'm from the universe. That's where I'm from. Okay, so we're gonna get started here pretty soon. I'm testing how long the delay is. Wow, it's like a 15 second delay. Wow. Use Inkscape for drawing. I don't have that. I have my iPad that I can actually show here, but I can't draw directly on the page itself. I mean, I could transfer it to a PDF and do it that way, and do it on my iPad, but that's a giant pain. You graduated from MIT? No, I couldn't even get into MIT. Okay, let's get started. So this first problem, we have a message that we want to send from, so the characters are PQRST, it looks like. The table, so we have some probabilities here, and if we have a message of 100 characters encoded using Huffman coding, then the expected length of the encoded message in bits is, and also I've never seen these problems, I'm going into this blind. Well, I'm not blind, but okay, so we got 4 different answers here, and they're really close to each other. So that tells you that you can't just do this, you can't just eliminate answers. You have to actually do the calculation. So this is how I would approach the Huffman coding problems. Work with me. So I'm gonna get my iPad out, and let's turn this on. So I'll block myself out for a second. So the way that I would approach this is, so we got P is 0.22, Q is 3.4, R is 0.17, S is 0.19, T is 0.08. So the idea here is that we're going to be making a binary tree of some kind, where the ones at the bottom here are going to be the letters that occur less frequently than the other ones. So how are we going to actually make this here? Let me actually see the chat so I can see it at the same time. So we can see here that this guy and this guy are the least frequently occurring characters. And one thing to note is that you can't have 2 characters occur simultaneously. So these are disjoint probabilities. So what we can do then is we can build the tree bottom up. So here, I'm going to have the R and the T be down here, and I'm going to join them together. So we can see that this node right here is going to have a probability of being 0.25 because it's adding 0.17 and 0.08 because they are disjoint probabilities. So then what we do then is now we're going to, you're exactly right, Rahul. So I'm going to eliminate R and T here, and I'm going to have R and T as one node, so to speak. So that's going to be 0.25, and then now we're going to do the same thing again on these 4 instead. Well, here the 2 smallest ones are 0.19 and 0.22. So that looks like we can put the P and the S down here and then join them up like this. So this guy right here is going to have a probability of, I think, 4.1, I think. Okay, so that's good. So then now I'm going to delete the P and S, that's right. So now we have P and S being a 1 node at 0.41 probability. So then now pick the 2 smallest guys, which are this one and this one again. So then Q is right here because Q hasn't been used anywhere yet. So now we're going to combine it with the R node. sorry, the RT node, which is this guy right here, which means that in total we have 0.59, I think. So this guy is 0.59. And then finally, we're going to combine these two. And obviously the top is going to be a 1.0 because these are just joint probabilities. So what we can do then is, because we have a binary tree here, this is a kind of involved problem, I'm going to assign a label as 0 goes left, 1 goes right. So 0 goes left, 1 right, 0, 1, 0, 1. So then, yeah, okay. So then how is the encoding going to work? Well, P here has, if we go from the root down, how do we encode P? We can just use 0, 0. So P is going to be 0, 0 in our encoding. Q is going to be a 1, 0, it looks like, 1, 0. Does right child or left child matter? No, because we're figuring out the number of bits, so it doesn't really matter the child labeling. The height matters. That's what really matters. I mean, I could have just called this 2. The height is 2. That's what I really could have said that. So I'll say height is 2. Q's height, well, the string is 1, 0, obviously, because we can just go take the 1 here, 0, to get to Q. And the height there is also 2, of course. The R is 1, 1, 0, and the height is 3 there. S is 0, 1, which has a height of 2, not 4. I almost put 4 there. And then T is 1, 1, 1 with a height of 3. Okay, so then what do we need to do here? Well, it says I'll actually shrink this. So it says if a message of 100 characters is encoded using this, then the expected length of the encoded message in bits is what? Well, then what we need to do is figure out the expected length for one character and then multiply by 100, because each character is independent of every other character, we're assuming. So all we really need is these numbers right here. Oh, and the probabilities. So I'm actually going to rewrite the probabilities right here. And what are they? So that's 0.22, 0.34, 0.17, 0.19, 0.08. So then what we need to do is the expected length is the actual length times the probability of it occurring for each of the letters. So the expected length is going to be 2 times 0.22 plus 2 times 0.34 plus 3 times 0.17 plus 2 times 0.19 plus 3 times 0.08. And I'm going to use my computer's calculator for that because I don't have one on here. So 2 times 0.22 plus 2 times 0.34 plus 3 times 0.17 plus 2 times 0.19 plus 3 times 0.08. And I find that this is 2.25. So then what I can expect here, so let me hide this. What can I expect here is the expected length is going to be 100 times what we found, so it's going to be 225. And in fact, that's what we get. Okay, so the whole idea is that we're splitting, we're joining up the least probable letters together into a joint node with the sum of their probabilities because they're disjoint. And then we just repeat until we have combined everything together. Then we look at how long each of the paths from the root is to each of the nodes, and we just do the probability times that height. That's the expected length, and if you add them all up, that's the expected length for one character, but we need 100 characters, so multiply by 100. Are you going to solve questions only of algorithms or data structure today? So I think it's only algorithms in here. Yeah, so only algorithms. I may do discrete and data structures at some point. So that one was actually a pretty hard problem. For those who are just joined, the link to the questions is in the description if you want to follow along. Okay, that was one problem. All right. So if you see the question, just immediately, you can immediately try to answer, because some of these are going to be easy. That first one was actually kind of hard, but some of these are easy. Okay, J had A as the answer. Okay, good. Consider a sequence of 14 elements. So we got a list here. Really look forward to discrete math. Thanks. If you have some resources, put them in the chat, like some links to questions and whatnot. The subsequent sum. So we have Sij going from, okay, so it's summing A sub k from I to j. Wait, that's not subsequence. That's yeah, that's not a subsequence, because a subsequence can be disjoint. Determine the maximum Sij. Okay, so it's the substring. So yes, the formula here says it must be continuous. So there's no reason to include the -5 and -10 at the front, because there's no positive elements before it. There's no reason to include the 0. So we better include the 12, because the -1 and the -9 are smaller than the 4 and the 12. So the 12 must be included, and the 6 and the 3 must be included for the same reason. So 6 plus 3 minus 1 minus 2 plus 13 plus 4 minus 9 minus 1 plus 4 plus 12. So I get 29. So I'm going to guess 29 here. Oh, okay, good. Yeah, so I think this one is just reasoning that the -5 and the -10 can't be used, or shouldn't be used, because they're before every, there's no positive elements before them, and the 0 at the end is useless. The -3 only hurts us. Okay. Array of 25 distinct elements is to be sorted using quicksort. Okay, so remember, quicksort is with the pivot thing. Assume that the pivot is chosen uniformly at random. The probability that the pivot element gets placed in the worst possible location in the first round of partitioning is what? So what do you guys think? We can actually eliminate 2 of the answers immediately. Just by saying the word probability, which answers can we actually remove? So we can actually remove C and D here, because it says probability. It has to be between 0. I guess we can remove, C might be true. C might actually be true, because it could be 100%, but it's not here. So, okay, we got 25 things. So the worst possible thing that can happen is that pivot becomes the end of the array. So that means every other element goes to the other side. So that means that It must be the minimum or the maximum. Okay, yeah, and it's distinct. Okay. So that means that the probability of getting the minimum is 1 in 25. And, oh, then maximum is 125 too. Okay, so that means it's 2 times 1/25, which is 8%. So it must be A. Okay, good. Okay, that was relatively easy. No decimal point in 1, that's not relevant. It 1 represents 100%, so it could be. Okay. Let's go to 4. We got n unsorted arrays. Assume that n is odd. Okay, that's weird. Because I see asymptotics here, so oddness I don't think really matters. Each of the, okay, I see from median. Okay, yeah, that makes sense. Each of them contains n distinct elements. There are no common elements between any 2 arrays. The worst case time complexity of computing the median of the medians of these arrays. Okay, so we're computing the medians of the n arrays, and then the median of those medians. Okay. Well, median can be done in linear time by the method often taught, which is like you partition the elements into 5 sets of 5, and then you recursively you work on the 5 and then recursively work on the rest, on each of the pieces. So median can be found in linear time. So the list of all medians can be done in n squared time because there are n arrays. So and then we incur an extra n from finding that median, but that's swamped by the n squared thing. Can we do better? I don't think we can do better. It says that there are no common elements, but that's not helpful because the array contents of one may overlap the contents of the other one. So it's not like that one array is uniformly smaller than another array. They could overlap, not have the same elements, but they're not. They could overlap. It's not that one is smaller than the other. So I think you have to do n squared. I'm going to go with n squared. Yes. All right. Although, as we saw yesterday, that many of these answers could be wrong, and the explanations could also be wrong. So that's just something to keep in mind. Okay. Just checking on some things. Okay. So D can be the answer. Yeah. There may be a way to do it faster, but there's no naive way to do it. Okay. Consider the following undirected graph G. Choose a value for x that will maximize the number of minimum weight spanning trees of G. And the number of minimum weight spanning trees for this value of x is one of these. Okay. So if x is bigger than 5, then x will never be chosen. So x is at most 5. So okay, so what if it's 1? Then I think you can get 4 spanning trees. I'm getting text. Well, so what if it's 1? So then we have 2 choices. No. Actually, no. If it was 1 in both cases, so if x is 1, both of the 1 edges will be selected. So then the only difference would be, and then the 3 would be selected because it's the next one up, and the bottom 4 can't be selected, so one of the other 4 will be selected. So the x one gets 2 spanning trees. So what if x is 2, then it's exactly the same scenario. If x is 3, because x is between 1 and 3 in that case. If x is 3, then both of the 3 edges will be selected, and the 1 edge will be selected. So then if x is 4, okay, so that's an interesting case. So the 1 and the 3 will be selected. The 5 will never be selected. So the x will always be selected to get to that node. Similar edges will be beneficial. I'm not sure what you mean by that. So if x is 4, the 1 and the 3 edge will always be selected. The 5 will never be selected because it's the heaviest one of all. If x is 4, it will always be selected because that vertex on the right has to be chosen. So the x will always be chosen. The 4 at the bottom will never be chosen. And so then we're back to 2 spanning trees again. So it must be, so let's look at 5. What if x is 5? So the 1 and the 3 will be chosen. The bottom 4 will not ever be chosen. Oh, there we go. If x is 5, then we have 2 ways of getting that rightmost vertex and 2 ways independently to get the leftmost one. Okay, so if x is 5, we can get 4 spanning trees. And if x is bigger than 5, we can only get 2. That edge will never be selected, so it doesn't matter. So it's 4. Yes. All right. Okay, good. So we see a bunch of explanations there. Okay. Consider the weights and values of the items listed below. Note that there is only 1 unit of each item. So 1 unit of each item. Okay, the task is to pick a subset of items such that their total weight is no more than 11 kilograms. So our max is 100 kilograms. 11, sorry. No item can be split, okay. The total value of items picked by an optimal algorithm is V-opt. A greedy algorithm sorts by value to weight ratios. Okay, so let's get out my iPad again. Go to a new page, make it up here. And then now we just need to see what the value of the difference is. So let's see. So let's figure out the optimal one first. So what is the optimal weight? So well, if I just pick the 10, I can only get 60. So can I pick the other ones in a way to get more than 60? I don't see it. Yeah, because I think the max you can get is 60. Because if I pick the 7 and the 4, I can only get 48. And I can't combine the 7 and the 2 and something else because I'm with less, and that only gives me 52. So the optimal is 60, it looks like to me. And then what's the value versus over weight ratios? So for 1, that ratio is 6. For 2, it's 4 because it's 28 over 7. 3 is 5. And 4 is 12. Okay. So then the greedy algorithm says we need to pick the items by maximum value to weight ratio. So that means we pick this guy first. So we pick this guy. Not 1. Should put first there. And then, so now, okay, so then the weight here is 11. No, 10. The weight here is 7. The weight here is 4. The weight here is 2. So that means we have to pick this guy, which means that we have used 2 of the weight. And then now we'll try to pick the one that is highest next, which is this guy. But we can't pick this one because we only have 9 weight left. So I can't pick this one. So then the next up is this 5, which we can pick because we have 9 weight left after picking this one, which means that we have we can pick this 4, which means that we have yeah. So that means we have 6. No, we have 5 weight left. Okay, so this one is second, which means that and I can't pick this one because this has weight 7 and I only have 5 left. Okay, so I have to pick these 2 bottom ones, which will give me a value of 44. So the greedy here is 24 for the first guy plus 20 for the second one, which is 44. And we can clearly see that the difference is going to be 16. Okay, good. When will you be doing discrete? Soon, hopefully. I have many other obligations I have to get to, so I can't do everything. Okay, so let me hide this. Okay, so this one is a more straightforward problem, I think. So we have functions here, and we want to arrange them in increasing order of asymptotic complexity. Okay. So the thing to keep in mind is that logs are always less than any power of n. N to any power is always more. Yeah. And yeah. And yeah, okay, that's fine. So let's see. So the first one in the list is either log 100 over n, 10, or 100 over n. So it can't be the log. I should say any power of n bigger than at least 0. Bigger than 0 is bigger than the log function. But if n to the power where the power is less than 0, then that grows less slowly. So then 100 over n is actually less than 10 because as n gets bigger, 100 over n gets smaller and smaller and smaller. Whereas the 10 never changes. So the answer is either B or D based off of that. Okay, then the answer should be B because look at B's and D's answer in the second position. The B one says 10 and the D one says log of n. Well, the constant function is less than a function that grows up. So the answer is B here. I don't even need to look at any of the other answers. Okay? Oh, by the way, if you have any questions at all, just put them in the chat and I will see them, although there's a delay. But I will get to them at some point. Okay. Okay, so let's go on to the next one. Okay, so this one is also looking pretty easy. So it looks like we're matching algorithms to design paradigms. So Kruskal's algorithm is greedy. So the answer should be either A or C. So then the difference gets down to quicksort and Floyd-Warshall. If you don't know what Floyd-Warshall is, I highly recommend looking it up. It's an idea of finding all pairs' shortest paths in a graph really quickly. It's really cool. So let's see. Where does quicksort go? Oh, quicksort is divide and conquer, yeah. Because remember quicksort, you have a pivot and then you put all of the elements that are bigger than it on one side, all of the elements that are smaller than it on the other side, and you recursively work on both pieces. You're dividing and conquering both of the pieces. So Q should go with 1. Oh, I'm a dummy. I forgot it was A or C. Q does go with 1. I meant A or C, and C is the only one that does it. That was just me being dumb and not thinking. Thanks, Barat. Okay. And I'm looking at my analytics, and it looks like we have over 1,000 views in the last 2 days. So thank you, guys. All right. So, okay, we got a connected undirected graph. The weights of the edges in E are positive and distinct. Is the minimum spanning tree always unique? Okay, so the weights of the edges are positive and distinct. So it makes me, so 1 is true because they're all distinct. Yeah, because if you have a different edge, it must have, and that you didn't pick, it must have higher cost than a one that you did pick. And they have the same number of edges. So so it's always unique. The shortest path between any two vertices is always unique. The shortest path between any two vertices is always unique. No, not necessarily, because you can have like a diamond diagram, for example, where the edges are all distinct. Oh, let me draw you a picture. So, let me show this up. So, if I have this graph right here, where I have S and T over here, it's not the source and the sink, I'm just making these up. And if I have 1, 4, 2, and 3, then the shortest path between S and T is 5. And I have 2 ways of getting there. And all of the edge weights are distinct. So I'm going to say that 1 is the only right answer here. Cool. Can you do a future video about practical problems that use these type of problems? Sure. Although I have so many things that you guys asked me that I am honestly overwhelmed, but I'll get to them at some point. Okay, let me take this off. So let A be an array of 31 numbers. That's a little suspect. Consisting of a sequence of zeros followed by ones. The problem is to find the smallest index such that A sub I is 1. Okay, by probing the minimum number of locations in A, the worst case number of probes by an optimal algorithm is what? Okay. Oh, okay, so here's something that you should notice. We don't, actually by the fact that all of these answers are small, you can't do linear search. So you have to do binary search. And it says the worst case here. So that means it's the log of base 2 of 31 and ceiling, which is 5. Okay, yeah. Okay, great. Yeah, so you can do binary search because if you query a point and it says, oh, this location 0, then you don't need to search before that because it's a sequence of zeros followed by ones. Yeah, and the array is sorted here. Yeah, the array is sorted, so we can do binary search here. Okay, so it's just letting you think, okay, you can't do linear search, so you must do binary search. This is unscripted and raw, thank you. Some of the questions in this list don't have options in the actual exam, just as an FYI. Oh, which ones don't? I'd be interested to know which ones. because I'd rather solve problems. Yeah, I'd rather solve problems without the actual answers there, so we can actually really think about it and see something hidden within there. Okay, so we got, so we're matching here. So we got towers of Hanoi with n disks, and from what I remember, that is exponential time. Yeah, and the only one that's exponential is 2 to the n. The reason it's exponential is if you expand the recurrence for it, it's exponential. Because you make 2 moves and then you reduce it to a size of n minus 1, so it's 2 times 2 times 2 n times. So it's P matches with 3, so it's either A or C. I better remember A or C here. Okay, binary search given. So what's the difference between A and C? So it's R is either 1 or 2. So let's see. Heap sort given n numbers in the worst case. I think that's n log n. Let's see. Addition of 2. Okay, that one's easier. Addition of 2 n by n matrices is n squared, no matter what. You can't do better than that, because that's the size of the matrix to start with. And you can't do better than linear time there. So S is going to be matched with 1. Yes. There's a PDF with all the gate questions sorted chapter-wise. Okay, if you can send that to me, I'd be really thankful. Okay, consider the recurrence function. Okay, so we got a recurrence function. So one thing about recurrence functions is when n is a constant number, it doesn't matter. So it's just when n is large, then the term actually matters. The 2 at the bottom doesn't matter. It's when the 2 t square root n. Oh, you posted the link, but it didn't actually show up. I think YouTube is filtering links. If you can send it to me on Discord or to my email, email's in the video description if you're not on Discord. Then I can look at it. Okay, so we have 2t square root n plus 1. Okay, so this is a little different than what I've seen. Okay. Well, I'm assuming that n is a power of 2. You can actually assume n is a power of 2 because if you take the square root of it over and over and over, you're going to get down to, you're never going to get a fractional number. And there's no flooring or ceiling here. So then it looks like we can apply the master's theorem, the master theorem. Okay, so let's do this. Yeah, in each branch is square root n, and there's only one step to combine them. I don't know of any algorithm that actually has that performance, so I think this is just asking you, do you know the master theorem? So it's really asking t of n is 2t of square root n plus 1 is another way of saying t to the 2 to the k is equal to 2 times t of 2 to the power k over 2, I think. Yeah, I think it's k over 2. Yeah, because if you take the square root, you have the exponent by 2. So I'm going to do a change of variables here. Yeah, so I'm gonna rename this to be t prime of x to be 2 times t prime of x over 2, where x is 2 to the k plus 1. Okay, so then now this is in a form that we know. So if you apply the master theorem here, what you get is, so then, yeah, so x is going to be, oh, no, sorry, no, that's not right. Is t prime of x. So that's going to be, because a and b are both 2, I think this just resolves to theta x. Doesn't it? Yeah, because this is the same thing as saying, if you look at this, it's log base b of a, where b and a are both 2. So this gets resolved to 1. So this is just theta x, okay. So, well, x is 2 to the k. So, yeah, so x is 2 to the k. And so the runtime is theta x. Yeah, so the runtime is theta of 2 to the k, where n is equal to 2 to the k. Okay, so then that means n is equal to 2 to the k, and we've seen this before. K is log n base 2, so that means it's theta log n. Whew, that one's actually quite difficult. So it's log n. Cool. Nice. If anyone has any questions, just put them in the chat. Let me turn this off. Okay. Consider the following C function. What's the time complexity? So the outer loop goes from 1 to n. So the outer loop does n iterations. The inner loop, okay, so this is, I see what it's doing. I wish you to get million and million of views someday. Keep going, you're amazing. That makes me feel good. Thank you. Okay, so let's see. The outer loop goes n times. So the inner loop goes n over I times because of theta of n over I times, which is j plus, because of the j plus equal I thing. So if the inner loop does n over I iterations, summing from 1 to n. Okay, yeah. Okay, yeah. So this is actually really asking you to remember a famous result that you prove in algorithms class. So I'm going to put this here, make it a little bigger. So what this is really asking, so one thing to keep in mind on these theory type tests is try to understand what is really being asked. Instead of just looking at the problem directly, look at what is really being asked. So what this is really asking here is to determine the sum from I equal to 1 to n of n over I. So why is this? So this guy right here is the outer loop, and this guy is the inner loop. So what we can do is, well, this n has nothing to do with the I variable, so we can just take it out of the sum right here. Oops, not I, it's 1 over I. So it's n times something. Well, what is this funny expression? This here is the harmonic number, if I remember right, and is approximately log n. And there are many ways that you can prove that. So the whole thing together is n times this guy, which is log n. So the answer should be n log n. Let's see. Yes. Okay, good. So let's keep going. Okay, so like yesterday, there are some things that you should just remember. This one you should remember. The running times of the main algorithms. So worst case for everything but merge sort, I think is n squared always. Yeah, so everything but merge sort, worst case is n squared. Oh, so it's this one. Yeah, merge sort is always n log n for worst case. So then, yeah, insertion is n squared, quick sort is n squared. Okay, good, nice. Let G be a complete undirected graph on 4 vertices, having 6 edges with weights being, okay. So let's gather this again. I guess at the rate I'm going, we're not going to get to 300 problems, but so let's just see how far we get. So we have a complete undirected graph on 4 vertices here. So it looks like a box with an X in it. Okay, so then we have, with 6 edges having weights 1 through 6, the maximum possible weight of a minimum weight spanning tree. Okay. So let's see. Well, wherever the one, so notice that the graph is symmetric. So it doesn't matter where I put the one edge. So let's just put it there, just as an example. Well, the minimum weight spanning tree will always have 3 edges in it, always. It will always have 3 edges. So if, okay, this is what this is asking. So note that a spanning tree can't have a cycle in it. So if I don't do this correctly, what I can do is I can have the 2 edge here and the 3 edge here. Well, notice that this doesn't create a cycle, and these are the 3 smallest edges, because the other ones are 4, 5, and 6. So, actually, that's not even one of the answers. So, what we can do is, if we can force the 1, 2, and 3 to be a cycle, then there's no way I can pick the 3 edge, no matter what. So, if I have the 2 here, so the 2 can't be here, but it could be any of the other ones. So then now let's put the 3 here to force it to be a cycle. So I can't pick the 3 edge, but no matter where the 4 edge goes, it can't create a cycle and is always connected to this other vertex. So no matter what I do, I have to pick either 1, 2, and 3 or 1, 2, and 4. So the most I can get is 7 out of this. Okay, good. That's the answer. 16. So G is an undirected graph with distinct weights. E is a particular edge. Which of the following statements about minimum spanning trees is true? Okay, so if E is the lightest edge of some cycle in G, then every MST includes E. So these ones, the details really matter for these types of questions. And if E is the heaviest edge, so let's have you guys answer this. So which of these 4 do you think? 1 is true, or 2 is true, or both, or neither? If E is the heaviest edge of some cycle, then every MST excludes it. Okay, I see. I see the answer. Okay. So let's let you guys answer this one. That's good. C, okay, so Manjot says C, they're both true. And for everyone watching, if you can recommend this stream or just the channel to everyone that you know who's preparing for exams like this, I would highly appreciate it. So magic is physics with tricks, says C, distinct. So each edge has a distinct weight, okay. Hey, are you all right? You look a bit sick. I think it's just the lighting. I'm all good. Already did. One only. Anyone have any other answer? And welcome to the stream, Anurag. Anuraj, I'm not sure how to pronounce that, sorry. Anything you say. Yeah. A. So it looks like everyone is saying A or C for this question. It's actually B. Dun dun dun. So why is this? So, I mean, you can read the explanation down here, but here's the reasoning behind it. So if you have a really, really heavy cycle, so like every edge is really, really heavy in it, then that means that if you have really light edges hitting the vertices from everywhere else, then none of the none of the edges in the cycle might be necessary. Because if they're really, really, really heavy and all of the edges coming into the vertices of the cycle are light, then there's no reason to pick any of the vertices in the cycle. So, and actually the example here is it shows that. But for 2, why is 2 true? It's because if you have some cycle in there, suppose that you did pick the heaviest one, then what you can do, because the graph is already connected, then there must be some other edge in the cycle that you could have otherwise picked that was lighter. So by like Kruskal's algorithm, for example, then if it was the heaviest edge, then that must mean that you've excluded some other edge in the cycle, which had to have had smaller weight because every edge has distinct weights. Okay. I'm practically in love with your efforts. Thanks for being born. That's hilarious. But okay, yeah, so this one was kind of tricky. Minimum spanning trees, you have to think about it a little bit more. Not more, a little bit. Because about like when edges are actually chosen in cycles and whatnot. So in this case, it happens to be 2, because 1, if you have a really heavy cycle with edges that are light coming into the vertices, you can pick all of those incoming edges and none of the ones within the cycle. Because you just need to connect up the vertices. You don't have to include, you don't include cycles, but you don't have to be really close about like 2 vertices. You can take a really long route if you wanted to, as long as the sum of all the weights is small. Minimum spanning trees are about a global optimization problem versus a local optimization problem. They solve the thing globally, not on a local level. So that's something to keep in mind. Okay, question 17. Assume that the algorithms considered here sort the input sequences in ascending order. If the input is already in ascending order, okay, so that's interesting. Which of the following are true? So bubble sort runs in O of n time because the input is already sorted. And note that this says theta, so it's not true that bubble sort runs in theta n squared time. So A and C can't be right. Merge sort never runs in theta n time, ever. So 3 can't be right. So it must be D. So 1 and 4, yeah. So in search and sort, you never have to do really any insertions at all. And quick sort is you always pick the pivot to be the first one, which is always the smallest one. And we saw that that was n squared before. Floyd-Warshall, for all pair shortest paths, is based on, okay, so I'll have you guys answer this one. So which of A, B, C, or D is this one? So is Floyd-Warshall greedy, divide and conquer, dynamic programming, or neither? So Magic says C, and yet, yes, that's right. And it's because it keeps a table of what the current shortest path distance is, and then updates it accordingly. And the reason is if you want to go from I to J, then you can go to any vertex otherwise in the middle. So then that means that you just look up what is the minimum one among those, and then update the smallest distance from I to J as a result. Yeah, so dynamic programming. Looks like everyone got that one right. That's awesome. Okay, we got 4 matrices here of different dimensions. Okay, the minimum number of scalar multiplications required to find the product using the basic matrix multiplication is... So this one you can actually, you don't even have to think about it, because the multiplications is just multiplying the sizes of the matrices. And since they're all multiples of 5, it must be A here. So it must be A here. Yeah, so Shivendra is right there. So it's N. Oh, no, it's not. Because, Sunny, what your question boils down to is it's N times the sum, half plus a fourth plus an eighth plus a 16th, etc. And that is 1. And if you actually think about it, if you think of n over 2 and then add n over 4 to it, then that's getting halfway to 1. And if you add an eighth to that, that's getting halfway to 1, and then it gets halfway every single time. So it's approaching 1. And you can prove it formally, but so Sunny's answer is n. Okay, the given diagram shows the flow chart for a recursive function a of n. Assume that all statements have constant time complexity. If the worst case time is n to the a, then what is the least possible value up to a? And of course, all the answers are almost identical. So I guess we have to we can't do eliminate answer. So let's see. So the thing with this is we're looking at worst case. So let's look at the longest possible path in this thing. So that means we start at the start and then take 1 a of n over 2. Okay, I see. So that means we take 1 a of n over 2 and then just take the next 2 to the right. There's no reason to take the left one because that's only 1, and we can find a longer path going the other way. So we get 2 going to the right, 1 going down, and 1 to the left at the bottom. So that means we have 5 instances of a of n over 2 in the worst case. Okay, so what this boils down to, so let me fix this. So what this boils down to is that we have a of n is equal to 5 times a of n over 2 plus little o1, because that's the time to combine everything. That's what it says the time complexity is. So because we have a is equal to 5, b is equal to 2, So that means that we have, yeah, so A of n by the master theorem is theta of n to the log of base 2 of 5. Yeah, because the A goes right here, B goes right here. And because this is just a constant function, so it doesn't matter. Okay, good. So that means that we need to figure out what log of 5 base 2 is. So I'm gonna take out my calculator on my computer, and that is 2.3219280. So it's 280. Okay, so it's A. Nice. Yeah, so this one is just looking at the worst case. So the other paths just aren't needed because it's looking at the worst possible case. Which of the following is the recurrence relation for the worst case time complexity of the quick sort algorithm for sorting? Okay, so it's worst case. So that the worst case is, remember, we split it with one element and everything else on one side. So that means that we should have a t of n minus 1, so A and D can't be right. And we don't have two instances of n minus 1, so it must be B. Good. Absolutely sorry if I can't pronounce that. I have a hard time pronouncing things lately, but anyway. Okay. So looks like we're going to be matching here. So we have Prim's algorithm. So Floyd-Warshall is dynamic programming. So Q is going to match with 3, I think. Yeah, and this is the only one, and C is the only one that answers that. So that's the good thing about having multiple answers here, is that you can actually eliminate other answers just by looking at one thing. So Q, which is Floyd-Warshall, has to match with dynamic programming. So that's C here. Sir, which path have you taken in the previous question? I think you mean 21, because I'm actually going to continue, but tell me what question that you're referring to. Set Yajit. Sorry, I can't pronounce it. So that I can go back. But I'm going to continue. Yeah, R matches with 4. Yeah. But the difference here is that Q matches with 3, which is all we needed there. An algorithm performs square root log n find operations. Okay. N inserts, square root log n deletes, square root log n decreased key on a set of data items with keys drawn in a linearly ordered set. Okay, so most of this is fluff. Which one of the following data structures is the most suited for the algorithm to use if the goal is to achieve the best total asymptotic complexity? Okay, so we gotta think, what is the time complexity for each of these? So let's look at unsorted array. 20. Okay. Yeah. So with this one, with 20, you just go the longest route because it's asking for worst case, and there were 5 instances of A of n over 2 along that route. That's the reason. And then I just used the master theorem. But for 23, so unsorted array, so magic says min heap, but let's actually be sure. So the find for an unsorted array takes n time each, so that's n times the square root of log n. Insertions, okay, so because it's unsorted, we just put them at the end, so it's just order n. The deletes takes n time each, So that's n times squared log n. And decrease key is just decreasing the value. So okay, so that takes just square root log n. So unsorted gives us n times the squared log n. Okay, that's good. Min heap find takes, in the worst case, n times, so that's n squared log m. Insertion takes log n each, so that gives us n log n. So min heap is already worse than unsorted array because this gives us n log n on the inserts. Sorted array, the find takes log n each, so the total is log n to the 3/2, so that's still better. Insertions take n time each, so that's n squared. Sorted array is worse, and the doubly linked list is worse because that takes n squared to actually in the worst case to find the thing. So it must be A. Well, that's pretty cool. I like that problem because it actually tells you in practice what is the runtime of this thing. Okay, so we're actually going pretty slow. So what I'm gonna do is I'm gonna stop at 2 hours, take a break, and then do another 2 hours, and then I'll update the thumbnail and the title for the number of questions we did. Okay, the graph shown below has 8 edges with distinct integer edge weights. The minimum spanning tree, okay. So it looks like we need to start drawing some things. Okay, so what do we have? So we have A, B, C, D, E, and F. 4, 6, 15, 2, and 9. And the other edges are not given weights yet. So the minimum spanning tree is, so MST, the weight is 36, and the actual MST is AC was picked, BC was picked, BE was picked, yeah, that's right, EF was picked, DF was picked. Okay. So the weight of the edges that we have here, 11, 26. Okay, so it is weight 36. Okay, so that's good. The minimum possible sum of the weights of all 8 edges of this. Okay, so this is determining what are the weights of the other 3. So let's see. So we couldn't have picked this one. So this is not 3. Could it be 5? Yeah, so this one can't be 5. Can't be 6. It can't be 6. Can it be? So this one has to be. This one has to be at least 10. Because then it would. Otherwise, it would have. This one would have been picked. So let's see. So it's at least 10. Well, what about this one? So this one must be at least 7. Because otherwise it would have been picked. Or, yeah, it must have been picked. And this one wasn't picked. Yeah, so this one must be at least 16 then. Because if it wasn't, if it was less than 16, then this one would have been picked instead of this one. And they're all distinct edge weights. So if this was 14, this one would have been picked. So I think this is the absolute minimum that I can do. So 10 plus 7 is 17, 33 for these ones. plus 36 is 69. And that's what absolutely Prignash is saying, and that's the right answer. Nice. So this is actually making you think, how does the MST be formed? How is it actually formed? What are the constraints on the other edges? That's pretty cool. So let me make this not visible. Okay. So let's see. So we have some algorithms to match. And go ahead and put the answer once you see them. So we got shortest path, I'm just reading your username. But thanks for joining. Dijkstra's shortest path, that is greedy, I think. B is definitely dynamic programming. So B, A, B, C, and D are not appearing here. That's kind of funny. B should be, so I'm guessing B is 2. So 2 should be matched. 2 should be matched with 2. So it's C or D here. Yeah, so it's not A and B because of that reason. Binary search should be divide and conquer, which it is. So the only difference is in 4. Backtracking search on a graph. So, okay, yeah. So it's depth first search. Backtracking search on a graph, you go down and then come back up, down and back up. So that must be depth first. So that must be 4. Okay, good. Yeah, so it's C. Suppose you're provided with the following function declaration. So we got a partition function. It treats the first element of A as a pivot and rearranges the array so that all elements are, okay. So it's the partition function for quicksort. And then we got k smallest here. So it's, okay, so left end is the partition. Okay, so the return value is the number of elements in the left part. Okay, so if left end plus 1 is equal to k, it returns the A, so that is the kth smallest. If it's bigger, then we need to recursively go on the first half. So this must be from, so A is being passed no matter what. The number of elements is left end. Okay, so if left end plus 1 is bigger than k, then the kth smallest is in the first half. So the number of elements we need to search in is left end. So so it must be A or B. Yeah, so it must be A or B because the left end is the start of these. And then if it's the other way around, then that means that it's in the second half. So the number of elements is n minus left end minus, oh, no, it should, oh yeah, it can't be a B, sorry, because we need to start the pointer at the beginning of where the second half begins. So that must be A, because the B answer starts it at the beginning and we want to start it in the second half. So it must be A here. I was asked, what is graph centrality in my PhD interview? What is graph centrality? Never heard of it. Really cool stuff. There are a lot of measures of what centrality means, but it's saying like what vertex is the most important. So if you have like one vertex that connects to two big chunks, then it's the center in some sense. A lot of the traffic passes through that one vertex. Or it could be that you have a lot of vertices that are connected to one vertex. So that one might be the center. So different definitions of what center means. Another cool one is onion decomposition. Search onion decomposition. You'll find a paper, which is pretty cool. Okay, so consider a disk that, do we still use disk? All right, that rotates at 15,000 RPM and has a transfer rate of, I guess that means 10 to the 6 bytes a second. So 15 million bytes a second. So if the average seek time of the disk is twice the rotational delay, and so this is something that I am not as strong on. If the average seek time of the disk is twice the average rotational delay, and the controller's transfer time is 10 times the disk transfer time, the average time to read or write a 512 byte sector is what? So okay, so let's see. So we can figure out the time to actually just write the data, not just find the position, but just to write the data. So time to just to write the data by itself. So we have 512 bytes divided by how long the rate of writing, which is 50 times 10 to the 6. That's seconds. Yeah, that's seconds. But what is the transfer time? Okay, so the controller's transfer time is 10 times the disk transfer time. So the controller transfer time is 10 times this one, because that's the time that the disk transfer takes. So what is the rotation? So so one rotation is so it's one rotation. Well, it's 15K rotations in 60 in 60 seconds, because that's the rotations per minute. So that is, yeah, let's see. So 15,000 divided by 60. So that's 250 rotations per second. Okay. So then what else do we need? So we need the average, so the seek time is twice the average rotational delay. So that's half of this. So that's so one rotation takes 4 milliseconds, I think. Yeah, because it's 250, 1,000 divided by 250. So this is 4 milliseconds per rotation. So the seek time is half of that, so that's 2 milliseconds. Oh, no, sorry. I have it backwards. So this should be, that's 4 milliseconds per rotation, but in the worst case, that's 2 milliseconds because to go to the other side. Because it could go either way, I guess. So the seek time is twice this number, so that's 4 milliseconds. So I think we just got to add these up. So let's see. So Okay, Bharat, thanks for joining. So let's see. So we've got 4 milliseconds plus 2 plus, oh my God, I didn't even show all the work I did. Yeah, so I did all the work already, and I didn't even show you. So 4 plus 2 plus 512 divided by 50 times 10 to the 6 plus 10 times that. So this should be but that's not any of the answers. 512 bytes. So what is yeah, that's 50, that's bytes. So 512 divided by 50 times 10 to the 6. So that's, oh, okay, I need to multiply by 1,000. Oh, okay. I was doing this in seconds, not milliseconds. Okay. Okay, so it's 4 plus 2 plus 512 divided by 50 times 10 to the 6 times 1,000 times 11. Okay, so that should be 6.1. Okay, yeah, I forgot to convert it to milliseconds. Okay, so that makes sense. Okay, let me take this off. Wow, thank you for all the views, everyone. It's really helping the channel out. Okay, so what problem we got here? Sir, if you can start a video series on compiler design, that'd be great. You're all asking me to do videos on everything. I wish I had the time to make all these videos in the mental capacity. All right, so assume that a merge sort algorithm in the worst case takes 30 seconds for an input of size 64. Which of the following closely approximates the maximum input size of a problem that can be solved in 6 minutes? Okay, so this is a reasonable question here. So let's see. So merge sort takes n log n time. So let's see. So if the runtime is n log n, and that takes 30 seconds. So for input of size 64, so it's some constant times n log n. So 64 log 64, okay, 512 I guess. 30 divided by 64 times log 64. So, okay, so that's the constant. And then now we just gotta solve for n log n where, okay. So let me get this out. So what we have here is C, some constant times n log n is equal to 60. Oh no, sorry, that should be 30. And the n here is 64. So then C is 30 over 64 log 64. So then we have to solve this for when we have, so how many seconds do we have? We have 6 minutes, that's 360 seconds. So 30 divided by 64 log 64 times n log n is equal to be 360. So if we divide, so, okay, so then let's see. So n log n is going to be 12 times 64 log 64. Okay, so I guess you would have to test the possible answers for this. because I don't think there's a way that you can solve for n directly. So 12 times 64 times log 64 is 1387. So 1024 times log, let's do 256 times log 256. That's only 600 something. 512 times log 512. Oh, that's it. It's 512. Oh, okay, yeah, you can do log of n to the n. Okay, yeah, you're right. I forgot about that. Yeah, so that'd be another way you can prove it, but I just plug in the answers here. Okay, so I'll take that off. Jesus Christ, guys, he's not a gate coach. He's a CS theory professor. Have some respect. You guys are duking it out in the chat. Funny. But really, it's no problem. I'm a content creator. You should ask things from me. That's what you're here for. So I'm not doing this for me. I'm doing this for you. So okay, let G be a connected undirected graph of 100 vertices and 300 edges. The weight of a minimum spanning tree is 500. Then when the weight of each edge is increased by 5, the weight of the minimum spanning tree becomes, okay. So this is a cool one, or at least this seems pretty cool. So notice that all the answers are almost the same. So remember that if you have n vertices, any spanning tree has n minus 1 edges always, because if you add another one, you'll create a cycle. So if you increase every edge by 5, then the weight of the spanning tree goes up by 99 times 5. And this answer is the only one that's a multiple of 5, so it must be right. That's actually pretty cool. Because each edge is increased by 5. If you didn't guarantee every edge, then you can't guarantee anything. I like that problem. There are 5 bags labeled 1 to 5. All of the coins in the given bag have the same weight. Some bags have coins of weight 10 grams, others have coins of weight 100 grams. I pick 1, 2, 4, 8, and 16 coins, respectively. Their total weight comes out to 323 grams. Then the product of the labels of the, okay. So let's see. Okay, so this sounds like a simultaneous equations problem, because like you have a certain number of each, you have a certain total amount that you picked, and a certain total number of coins total that you picked. So let's let X be the number of weight 10 coins, and Y be the number of weight 11 coins. Well, the total that we got was 323, so 10x plus 11y is 323. Let's see, so what else can we get? So the total number of coins we picked is 31, because it's 1 plus 2 plus 4 plus 8 plus 16. Yeah, it's 31. So the total number of coins we picked is x plus y, but that's 31. Okay, so then we just do, this really isn't algorithms, but I'm just gonna solve this anyway. So if I multiply everything by 10 on this guy and subtract the 2 equations, what I'm gonna get is the x's go away, which is what we want. We end up with y is equal to 13. And then x must be 18 then, I think. So then the product of the labels of the bags having 11-gram coins Yeah, so we pick 13 coins here of weight 11. Okay, so the 13 can't be, can it be in 5? Well, it can't be all in 5 because it's 16 coins. Okay. Oh, all coins in a given bag have the same weight. Okay, great. So then that means that we must find a subset of these that add up to 13. Oh, this is cool. Think about it. These are powers of 2. So this is really asking, can you make a binary number which is 13? And we actually can, because we can have 1, 4, and 8. That corresponds to 1, 0, 1, 1, 1, 0, 1 in binary, which is 13. Oh, that's kind of cool. So it's 1, 4, and 8. So that corresponds to bags 1, 3, and 4, which is a product of 12. So the answer should be 12, I think. Yes! Nice. Cool. All right. Looks like we got P, NP, and NP complete. Suppose a polynomial time is discovered that correctly solves the largest clique in a given graph. In this scenario, which of the following represents the correct Venn diagram of P, NP, and NP complete? So largest clique, you have to form into a decision problem, but that problem is NP complete. So if you can solve that in polynomial time, because it's NP complete, everything in NP is now NP, because it's NP complete. So we should have P is equal to NP, and since this problem is NP complete, we should have NP complete being equal to P. Actually, no, that's not true. Generally, yes. Okay, so I would assume, I'm going to guess D here, but this is not actually right. So D here is not right, okay? I'm guessing that's what they wanted you to answer, but it's not right. Sigma star and the empty set are never NP complete. They cannot be NP complete. So NP complete must be a subset of, sorry, it must be a subset of P in this scenario. Okay? And I can give a reason why that's the case. Sigma star, which is every string, and empty set can never, ever be NP complete, ever. Okay? So C is technically the right answer, but the answer that they want, I'm guessing, is D. Yeah. Because of those corner cases, I'm guessing that's not really that important, but yeah. Okay, so we got some comparisons, minimum number of comparisons required to find the minimum and maximum of 100 numbers is what? Okay, I'll have to think. How many can you do? I do vaguely remember something like 3n over 2, which is 150 here. But, oh, we don't have to compare the first element to itself. So we can subtract 2 because we're searching the minimum and the maximum. So it's 3n over 2 minus 2. So that should be 148. Yes! Nice. Good. We should revisit this question later at some point. Okay, it looks like we're going to try to get 50 questions done in 2 hours, and then we'll take a break and then do 2 more hours. Which of the following, unless you guys don't want to hear me blabble on about algorithms for much longer. No one should have to listen to me. Okay, no, I'm kidding. Which of the following correctly determines the solution of the recurrence equation with, so t of 1 is equal to 1 doesn't matter. The constant term never matters here because we're just doing asymptotics. So t of n is equal to 2 n over 2 plus log n. So here we have, so log n is different. So here, so let's get our little thing out. Okay, getting notifications. So we have t of n is equal to 2t of n over 2 plus log n. So we can't apply the second version of the master theorem anymore. So we have to apply the first case. Okay, so I have to remember back to the master theorem days. It's been 7 years since I've been taught this stuff. So I know that so A is equal to 2 by this, B is equal to 2 by this. And let's call this f of n. So, okay, I'm gonna have to Google master theorem because I don't remember it. Yeah, so if it's, okay, so the critical exponent is log b's, okay. Yeah, log b of a. Okay, so since log n is bigger, that must mean we need to apply the first case. Yeah, the first case. So case 1, if I remember right, is t of n is, yeah, it should be, it's theta of, is n to the log base b of a again, I think. Let me look that up again. So f, yeah, it's n to the log base b of a, yeah. Yeah, so that here is n. Okay, yeah, so it's n. If this function is n to the log base b of a exactly, then you add a log n term here, and then otherwise it's gonna be dominated by this term. Okay. So this should be n. Okay, good. Yeah, I need to remember the master theorem better. So let's go down. Consider two strings, whatever those strings are. Let x be the length of the longest common subsequence between a and b, and y be the number of those longest ones. Okay. So subsequence. God, I hate questions like these. So x must be 3 because no, y should be 3 because the tens digit in all the answers is 3. So y should be 3 no matter what. So we don't even need to focus on y. So we need to find a subsequence that a length of a subsequence that occurs that occurs 3 times. So remember that subsequence is contiguous. So not necessarily contiguous. So QP, I can't do all 5 digits of A, letters of A. Can I do the first 4? QP, QR, okay. So I can, yeah, I can do 4. So we have to look at the length 4 subsequences of A, and there are only 3 no, there are 5 of them. So QPQR, so that's 1, because that appears in B as QP blank QR. The other QPQR is the same in A. QPRR, that appears in B, so we're up at 2. QQ... Oh, no, I have it wrong. X is 4. Yeah, I'm dumb. This message is held for review. Are you guys spamming the chat? No, I'm kidding. So X is 4. Because the length of the subsequence is 4, because I can't do 5. Okay, that's good. What did you guys write? Apparently someone wants to post hotgirls2020.com. That clearly has to do with algorithms. All right. Suppose PQRST are sorted sequences with certain lengths. They are to be merged into a single sequence by merging together 2 sequences at a time. The number of comparisons that will need it in the worst case by the optimal algorithm for this is what? Oh, okay. So what we should do here, oh, I accidentally put hide on your comment, Rahul. Sorry about that. I clicked the wrong button by accident. Okay, so what we should think about here is we're merging, we should merge the smaller lists first, because they're going to be re-merged with bigger lists later. So it's kind of like the Huffman encoding thing. So the 20 and the 24 should be merged first. So the 20 and the 24, 24, those should be merged. So this has a cost of 44. What is the number of comparisons? So that's 44 minus 1, because we don't compare the first element. Okay. Then we have 30, 35, and 50. So that means we should combine these 2, I think. Yeah, we should combine these 2. So this has a cost of 65 minus 1. Then we should combine the 44 and the 50. So that'll give us a cost of, that should be 94. Yeah, 94 minus 1. And then the 65 minus 1 can merge to here. So the sizes of the lists are 94 and 65. So then it should be 94 plus 65 minus 1. So I guess it's just, it's adding this one, this, and this, whatever that is. So this should, oh, went away. So I'm just going to add them up on my computer. So 43 plus 64 plus 93 plus 94 plus 65 minus 1 is 358. Yes! Nice. Okay, the thing to realize there is that smaller lists are going to be combined first. Should be combined first because they're going to be compared at a later point. So I should turn that off. Okay, the number of distinct minimum spanning trees. This isn't really asking about algorithms. It's asking about specific instances and understanding the algorithms, which is, I guess, it's fine. The number of distinct minimum spanning trees. Okay. So let's see. So let's actually draw this graph and actually put in the edges that have to be chosen no matter what. And that might give us some ideas. For those who don't know, this graph right here, if you complete it, is called the wheel graph. So 2, 1, 2, 2, 1, 1, 2, 1, 2, 2, 2, 2, 1. So this edge will always be selected because if I pick the other two, it will have a higher cost. This edge is always selected because it connects everything up. Either one of these could be selected, I think. So let's see. Does this edge have to be selected? Yeah, okay, so that edge has to be selected. Because if I connected it with two other edges, that would have a higher cost no matter what. Does this edge have to be selected? Yes, it does. So this edge has to be selected no matter what. Which means this edge has to be selected, which means this edge has to be selected. Which means that, well, neither of these could be selected. So I can't pick those two. Oh, there we go. So any one of these three can be selected independently, and any one of these two can be selected independently. Oh my god, I'm so sorry. Okay, so let me actually go through this. So I'll actually go through the whole thing again. So this is the graph that we have on the screen. Let me make it a little bigger. So what I'm going to do here is I'm going to pick the edges that have to be selected in a minimum spanning tree no matter what. Well, we can see that this one edge over here has to be selected. Why? Because if I pick the other two, that would have a higher cost than picking the one and one of these two edges, because that would have cost 4 versus cost 3. This 2 edge has to be selected no matter what, because there's no other way to connect these two. This one edge has to be selected because if I pick any 2 other edges to get these 2 vertices, then that would give me a higher cost again. So this has to be selected. For the same reason, this edge has to be selected. Because if I don't pick that one, then I have to pick 2 of the 2 edges, which is going to give me a higher cost again. So this edge has to be selected. But then now, if I don't pick this edge, then I must pick one of the 2 edges, which is going to give me a higher cost. So I have to pick this edge. But in order to get to here, if I don't pick this one, then I have to pick one of these two edges right here, which is going to give me a higher cost again. But then now, so we say, okay, well, there are two edges I can pick here. Any one of them are fine. Any one of these three edges is fine. Any one of these two edges is fine. Except these two edges can't be selected because they'll create a cycle. Both of them will create a cycle. So I can't pick those two edges no matter what. So actually those two edges will never appear in any minimum spanning tree of this graph. But now I have these three, which none of them will create a cycle. These two can't create a cycle. I can't pick both of these or any two of these because they'll create a cycle. So I must pick one from here and one from here. But because those choices are independent, now I have 3 times 2 different possibilities, which is 6. So that's why I get 6 here. Okay. It's actually a pretty nice problem. It takes a little bit of work to get it, but it's pretty cool. Okay. So I'm actually going way slower than I thought I would be going. Okay. So we got a rooted tree here with vertex labeled P as the root. Okay, so I'm getting a warning on the stream that it's lower quality than they expect. Okay. Okay, sorry, I'm getting notifications. P is the root here. The order in which nodes are visited during in-order traversal is, so remember, in order is the left, you go left recursively first, then the root, then going right. So then that means that P goes left, Q is now the root of this subtree. Well, there's only one child, so we go to S. So S is first, then P, because we've explored the left half. Sorry, Q is next. So yeah, all the answers have S, Q, and P in order. So now we get to R. R is the root node. Then, so that means we go left. Then that means we do T. So SP, SQPT, which is what all of them have. So then now we go to the root. But it has 3 children. So which one do you do? Because it could go... Oh, okay. I see. So if we're doing... So there are 2 things that can happen. It could either be left, root, middle, right, or left, middle, right, left, middle, root, right. So the middle and the root can have 2 possible orderings. So if the root is second, so then that means that T is explored, so SQPT, well, all of them have that. Then we skip R for now, we go to U, which is the new root, then we visit W. So none of the answers have W after T. So then that means that the ordering must be left, root, middle, right. So R must be the next one after T, so that's only answer A or D. Yeah. Oh, actually, no, C could be right. No, C can't be right because R is processed last. So, yeah, so it's not C. So, T, W, U. Yeah, your ordering magic is it could be right if that's the ordering, but that's none of the answers because the R, because either the U and the W in the wrong order or R and V are in the wrong order. So it's either A or D. So R is next, then U is the root, but it's not visited yet until it does the W child. So TRW. So it must be A. Sweet. Okay. Suppose depth first search is executed on the graph below starting at some unknown vertex. Assume that a recursive call to visit a vertex is made only after first checking that the vertex hasn't been visited earlier. Okay? Then the maximum recursion depth, including the initial call, is, okay. So we're gonna have to think here. So the middle node that's sticking up can never be visited in the longest recursive call, because if you go up that, then you have to backtrack, but you can't do that. Did you get any wrong until now? Nope. I'm 100% right so far. Well, actually, I accidentally selected the wrong one, but that's my mistake. I got the answer right, but I selected the wrong one. So this top middle vertex can't be selected. And I don't think the rightmost vertex can be selected. So, but if you do a zigzag pattern on the two sides, what do we get? We get 1, 2, 3, 4, 5, 6, 7, 8, 9. Middle bottom vertex is 10. 1, 2, 3, 4, 5, 6, 7. Yeah, so I think you have to get 19. And you can't, well, we can't get 22 because there are only 21 vertices here. So 22 is not right. 21, you can't visit either of those vertices, so it must be 19. Yes. All right. Cool. And if you guys have any questions at all, feel free to just drop them in the chat. Don't wait for me. Feel free to put any doubts you have about any questions in the chat. Okay, you have an array of n elements. Suppose you implement quicksort by always choosing the central element of the array as the pivot. Then the tightest upper bound for the worst case performance is. So central element here means the middle of the array, not the middle element, not the median. If you pick the median, then it would be n log n. But it says it's always picking the central element because the array is unsorted. So you would have to get n squared then. Sweet. Yeah, because the worst possible thing is that it's either the max or the min. All right, so let's do this question and then we'll take a 10-minute break and then do more. Suppose we have a balanced binary search tree holding n numbers. We're given two numbers L and H and wish to sum up all the numbers in T that lie between them. Suppose that there are, oh, so it's a binary search tree, okay. Suppose that there are m such numbers in T. Then if the tightest upper bounds that we can compute the sum is, okay. So we got different powers here and so this immediately tells us just by looking at the answers that D is 0. And that makes sense because m is the number of elements and it takes constant amount of time to add one element. So C should be 1. It is in every answer. In fact, B is 1 in every answer. So the answer is whether A is 0, 1, 2, or 3. Oh, A is 0. Because all that you need to do is to find where L and H, like the smallest number that's bigger than L and the biggest number that is less than H. So you have the range right here. Let's just see if So you have a range right here. Well, you may not have the elements L and H exactly in the tree. So what you do is you find the smallest one that's slightly bigger than the low end, and the biggest number that's smaller than the top end in the tree. Well, each one of those takes log n time to find, but doing the search, going from that point to another point takes m time, because you take constant amount of time per number to find. Okay, so A should be 0 because all you need is the log n performance to find the number, the beginning and the end, so to speak, of the numbers to find. And the other numbers between them, because it's a binary search tree, because it's a binary search tree, you you don't need to do any more searching. I actually already said that. So it should be A is 0, so it should be 110. Yes. All right. Cool. So what we're going to do is we're going to take a 10-minute break. We'll come at 10 after the hour, or at least in 10 minutes, and I'll see you all then. Thanks. All right, let's get started in a little bit. So what I've decided during the break is there's no way we're going to get to 300 problems really quickly. So what we're going to do is let's just have this session go all the way until we hit 100 problems, however long that takes. And that would be a nice title. 100 problems solved. Okay. Okay. So I don't see any other questions in the chat. So let's actually continue. So we got a hash table here with 100 slots. Collisions are resolved using chaining. So for those who don't know, if you put something into the hash table with chaining, it just makes a chain if you put it into the same place as something else. Assuming simple uniform hashing was the probability that the first 3 slots are unfilled after the first 3 insertions. So because it's using chaining, so the probability of being in one place is 1 over 100. And since it's using chaining, it's the probability of not hitting those first 3 is 97 over 100. But because it's using chaining, it must be the same probability each time. So 97 times 97. Okay, so it should be A. And the order doesn't matter. Yeah, so it can only be A. Okay. It's because it's using chaining here. Okay. Consider the pseudocode right here. Function do something takes a root, and each node of the tree is the type tree node, which is when the pointer's return of the root is passed in as the argument to do something, the value returned to the function corresponds. Okay, so it tells. So we got to analyze what the function does. So value 0. If the left is null, value is 1. Value is equal to do something. So if it doesn't have a left child, no matter what value it is, it's... Oh, no, never mind. It's not a for loop. Okay. So if there's no left child, then it gives you 1. Value is equal to do, otherwise, if there is a left child, you recursively do the left, and then you add on the right side. So what is this? So it's not the number of internal nodes, because it only adds it if you're at the bottom, so to speak. The height of the tree. No, because it can't be the height because it's adding what you do going left versus going right. So it's not the height. Number of nodes without a right sibling. No, because it's adding the value onto the right sibling. So it's the number of leaf nodes. Oh, nice. Cool. So it's the number of leaf nodes. Consider the C function below. God, C is awful. It's just a pain in the ass to deal with. So process array, okay. Which of the following statements is correct? So let's see. It will run into an infinite loop when X is not in list A. So let's see. Okay, so assume that the array is sorted in ascending order. Okay, so it looks like we're doing binary search here in some sense. So if X is equal, so if X is not in there, no, because there's a while loop, and I will become bigger than J at some point. So it's not A. It's an implementation of binary search, maybe. Let's see. It will always find the maximum element in list A, no, because you pass in these other parameters. It will return -1 when X is present in list A. No, because, yeah, it's doing binary search, yeah. Because it returns -1 if it's not equal to it, and it's sorted in ascending order. Okay, so yeah, it's binary search. Excuse me. Which of the following is the tightest upper bound for the number of swaps required to sort using selection sort? So, number of swaps. Okay, so this is not the number of steps. This is the number of swaps. Okay, yeah, so this one you have to be careful of, because when you find the next element to move and then swap it in using selection sort, then you will make one swap per element. So that means the number of swaps is linear in the list because you're making one swap per element. So it must be B. Yeah, that's not the runtime, it's the number of swaps, which is a different measure. What's the time complexity of inserting an object into a binary search tree of n nodes? The worst thing that can happen is that it's like a linked list, so you have to insert it at the bottom. It's not balanced. It doesn't say balanced here, so it's order n for that. Oh, look, regular languages. All right, my favorite. Consider the languages empty set and L2 being a single. I think we answered this one last time. So L1 is empty set. So L1 concatenated with anything is empty set. So then it just depends on what L1 star is, and that's just the set containing the empty string. So let me go through that again. L1 is empty set. So L1 can be empty set concatenated with anything, which is L2 star in this case, is always the empty set. So it's empty set union L1 star. So the answer really is what L1 star is. And by the definition of what star is, the empty string is always in the set of the star of any language. And so therefore, it must contain the empty, it's the empty string, or the set containing the empty string. If you want more details, feel free to put something into the chat if you don't quite understand it. What's the time complexity of Bellman-Ford's single source shortest path on a complete graph? Okay, so Bellman-Ford runs in VE time. So a complete graph has n squared edges because it has every possible edge. So that means it's V times E, which is n times n squared, which is n cubed. So that should be n cubed. Yeah, A was for the other question I did. Okay. Why not phi? I'm not sure what you mean by why not phi. Phi here means empty set in regular language, finite automata type terminology. Oh, I'm not sure what you mean by why not phi. I'll have you answer that while I continue. Consider an undirected random graph of 8 vertices. The probability that there is an edge between a pair of vertices is 1/2. What is the okay? So this gets into like random graph territory, which is kind of cool stuff. So let's do this. So let's see. So this is asking, okay, so let's look at a given triple of vertices. So this is asking, what is the probability that all 3 edges are present? Because that's a cycle of length 3. Well, this is a probability of 1/8. because all three edges have to be there, and each one occurs independently with probability a half. So therefore, the probability that a single triangle appears is 1/8. But how many triangles are there? So the number of triangles is, well, the number of vertices, choose 3 potentially. So it's 8, choose 3. And so the expected number of triangles is equal to 8, choose 3 times the probability that each one appears, which is 1/8. So then now I gotta refresh my combinatoric stuff. So that's 8 factorial over 3 factorial, 5 factorial times 1/8. The 8th and the 8 cancel to give 7 factorial. So then that 7 and 5 factorial reduce to 7 times 6 over, well, 3 factorial is 6. So this gives us 7. So I'm going to guess 7. Nice. Okay, so you answered the other question. So let's see. Let me turn that off. So why not B? It's because of the L1 star here. If it was L1 without the star, then you'd be right. It would be, how is empty set star the empty string? It's mainly because of the definition of what star means. Star means reaching into the language and picking out strings from it and concatenating them a certain number of times. The reason that empty string is in there is that corresponds to 0 times. So picking a string 0 times, well, you're left with the empty string. So that's why empty string is in there. We can't fit any other string in there because the empty set has nothing in it to pick, no strings to pick. I can't pick one string out of the empty set because the empty set has nothing in it. So, all right. Which of the following statements is true for undirected graphs? So I'll have you guys answer this one. So which one of these is true? So A, B, C, or D? Let me check something real quick. It's pretty awesome. Both, and you're right, Magic. So why is this true? If you add up all the vertex degrees, well, every edge corresponds to two vertices. So that means when you're trying to count the degrees of them, then you're going to include every edge twice. So the number of edges times 2 is what you're going to get. And what about the number of odd degree vertices is even? So, why is that true? Well, if the number of odd degree vertices is odd, then that means that the total degree is odd, which can't happen. So, the line graph is, so what you take is you have one vertex for each edge in G, and for any 2 edges that are next to each other, you have an edge between those 2. If they're incident with the same vertex. Which of the following statements is true? The line graph, okay. So let's actually look at these one by one. because I actually don't know the answer ahead of time. So let's look at a cycle. Then what we're going to do is we're going to take the purple points are the edges in here, and we're going to make an edge between these if they are if they're incident to one vertex. So like this one and this one are incident at that vertex. Sorry. So this edge and this edge are incident at this vertex, which means that we're going to make an edge between these. And similarly for the other one. So you can actually see that the line graph of a cycle is a cycle. Okay, so let's see. So let's look at the cleave one. And this will always happen because in a cycle, a vertex only involves two edges. So those two edges will be incident to each other and no others. So the line graph is a cycle. What about a clique? So if we have a clique here, well, we can't do 3 vertices. Maybe it might be false for 4. So if I make a point for all of the edges, oops. Yeah, this is a hard one. This is surprisingly hard. So maybe not do it this way. So let's put a dot in the center. So we'll form these ones on the outside. We'll form that one, that one, that one, that one. That one. Yeah, so for 4 it works. What about for some? I'm not sure about clique. I'm not sure. So let's do the planar one. I'm not sure. So for planar, the number of edges is always at most 3 times the number of vertices minus 6. And there's a lot of results proving that. But so let's see. So if R is false, I don't know. Line graph of a... Okay, so let's try a planar graph. well, it can't be just 3 vertices. It's got to be more. And there's no reason not having every single edge that we can present. Okay. So if I form the points, which are going to be each of the edges here, so what is the degree of each of these? So the degree of this top one is 5, it looks like. The one on the left is 4. This bottom one is 5. One, two, three, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 on this one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Looks like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So then the total number of edges will be 14, 24, 30, 36, 42, 46, 50. So the total number of edges will be 25. 1, 2, 3, 4, 5, 6. Oh, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, that's an example. Yes. Yes. Why? Why is it an example? So the line graph here has 10 vertices, because that's the number of edges here. But adding up the degrees and dividing by 2, that's the number of edges that we can get. So the number of edges is 25, because the total is 50 divided by 2. Well, here, the total number of edges to be planar is 30 minus 6, so that's 24, but I have more vertices, so it can't possibly be planar. So R is false. So now it's just wondering whether Q or S is true. Okay. So is Q or S true? Well, let me turn it off. Line graph of a tree is a tree. Okay. Maybe it just involves counting the vertices. So if a clique has n vertices and it has n choose 2 edges, so then that means that the line graph has n choose 2 vertices, because each one for each edge in the original. Oh, I turned this off, sorry. Has n choose 2 vertices. Well, each one of those edges is incident to n minus 1 on one side and n minus 1 on the other side. So the total degree, the total number of edges is n minus 1 times n choose 2. Yeah, that's way less than what is necessary. Okay. Because what we would expect is n choose, so we should expect is n choose 2 choose 2. So that's roughly like n to the 4th, whereas this is like n cubed. So Q is not true. Okay, that's a really hard problem, so it must only be B. be P. Wow, that's a hard problem. How you guys doing out there? Still hanging in? Okay. So we're halfway done. God. Number of elements that can be sorted in log n time using heap sort is, let's see. Well, to sort n elements, it takes n log n time. So to sort, so how many elements can be sorted in log n time? The total time takes n log n. Well, theta 1 is too small. So log n is too many because that number, log n times log n, is too much time. That's more than log n time. So it's either B or C. What about B? So square root log, so that's like n to the, yeah, square root log n times log of the square root. No, that's too many. That's too much. That wouldn't even match log n time, so it must be C. Okay, yeah. So I guess this one is just plugging it in. What is the return value of FPP? So it's the same, where if P is initialized to 5 before the call, note that the first parameter is passed by reference. This is not really algorithms, but okay. Okay, so X, so they're both 5. C becomes 4. The if isn't taken. So X goes up by 1, so, okay. It might be worth to write it out. So f of 5, that's going to be f of 6, 4 times 6. And this will give us f of, oh, okay, because it's passed by reference. Okay, so it's going to be modifying the value for the return at the end. So the only thing that really matters is let's go down to 0. So we add 1 to x every time. So it started with 5, then it becomes 6, 4, 7, 3, 8, 2, 9, 1, and then, so on 9 and 1, C becomes 0. So f of 9, 1 returns 1. So then, so x is 9 now. So the call up returns 1 times 9. And then I think it should just be powers. It should be 9 to the 5th, shouldn't it? So what is 9 to the 5th? Oh no, not quite. That's not one of the answers. Oh, it only went up by 4, not 5. I'm a dummy. 6, 5, 6, 1. Is that one of the answers? Yeah. It'd be because x's value doesn't change on the recursive calls. It changed before the recursive call took place. So x should be 9. It recursed 4 times, so it should be 9 to the 4. Yes! Nice. Okay, pre-ordered traversal of a binary search tree is this. So that's root left right. Which of the following represents a post order? Okay, so let's just build the tree itself. So let's see. So 30 is the root. Then it says left, right. So 20 must be the root over here. And 10 should be the root of this. And it's a binary search tree, so we gotta worry about that. Then 15, it must be to the right of 10. It can't be the left of 10. So 15 should be over here. 25 should be on the right side of 20. It can't have anything to do with 15. So the 25 should be here. Then 23 is bigger than 20 but less than 25, so it should be right here. Then 39 should be the root of over here. And then 35, 42, which are all bigger, so it should be like this. So the post order should be left, right, root. So left, left, no left, right. So 15 should be first, so it's B, C, or D. Then 10, so it should be B or D. And then what happens? So root, and then we got to go to right, and then left, so 23 should be next. Oh, so it should be D. Okay, so it's just reconstructing the tree and then doing the actual post order on that. Okay. Consider the following operation along with NQ and DQ operations on queues. While Q is not empty, DQ. What is the worst case time complexity of a sequence of n multi-DQ operations in an initially empty queue? If it's empty, nothing will happen, though. Oh, this question is really easy because the while loop will never execute. So that means it's just an order one operation per multi-DQ. And so it just gives one for each. So, and there are n of them, so it's n total. Okay. That one should be easy. Assuming P is not equal to NP, which of the following is true? So the first one is not true because of something called Ladner's theorem, which says that there are problems between P and NP complete. There's nothing in intersection between NP complete and P. That's true. NP hard is not equal to NP. Don't get that confused. NP hard is not the same as NP. And D is definitely false. So it's B. Let WN and AN denote respectively the worst case and average case running time of an algorithm. Okay, so this is just asking you, do you know the run times? Oh, okay. Thanks. Sorry about that. Okay, so it's which of these it is. So A of n is average, so it should be less. But it could be the same running time, but it can't be more. So I think it should be C, because it's either C or D, because the other ones, it can't necessarily be the same, and it can't necessarily be the same or more. It could be less. So it's one of these two, but the little o, it could be exactly the same running time. So it's got to be C. Consider the quicksort algorithm. Suppose that there is a procedure for finding the pivot element which which contains at least 1/5 of the elements. But okay, so it's just finding the asymptotics. So if it's at least 1/5, so then that means that the other piece is 4/5. Okay, yeah, so it should be B. Because one of the subproblems is size n/5, the other problem is at 4n/5. Isn't in Q40 we can find the in order in n time? Then ln h and log n time. Yeah, it is order n, but the thing is that there was a different parameter m being passed in. And so it was log n, because that's the number. So the m being passed in has nothing to do necessarily with the number of elements in the tree. If it was n, then you would be right, but it's not. So, because m could be really, really, really tiny compared to n, but we don't know anything about it. The subset sum problem is defined as follows: given a set of positive integers and a positive integer w. Okay. An algorithm Q solves this problem. Oh, yeah, your answer of ON could be right. Yeah, that's absolutely true. It could be right. It's just yeah, it's not the actual specific answer that we can get, the most specific answer. Okay, so this is asking about this pseudo-polynomial running time. So Q solves the subset problem in polynomial time when the input is encoded in, okay, which of the following statements is false? When it's encoded in unary, then it is polynomial. This is actually kind of a hard problem. When it's encoded in binary, it's not in polynomial time, because if W is in binary, the running time is depending on the value of W, not the size of W. It belongs to NP. It is NP hard. So B is the wrong answer. It is false. So that's the one we pick. Question 59. So we got a directed graph here with negative edge weights. Which one computes the shortest distance? So if there are no negative edge weight cycles, then it should be right. Okay, from vertex A, okay. So A to B, that's 1, and we can't use any of the negative edge weights in our favor. Oh, well, we can be certain that it's right. Why? Because none of the negative edges go backwards. They only go one direction. So, so once you go to the right side, you can never go back and do another negative edge weight. So it must be every vertex, I think. Okay. Okay, this one's pretty easy. Merge sort uses divide and conquer. We've done that before, where you divide it into small pieces and then merge all of the small pieces and then build and build and build. So it's divide and conquer. A postfix expression for the infix expression is, so let's see. So for this, you need to work inwards. So the most inner expression is the C plus D here. So plus must be the end, so it's not A. And then what do we need? And then left to right. So then with times and divide being more priority. Oh, so the times isn't the second to last thing on any of these. So it should be none. Let's go over that. So plus must be last because it's the most inner expression, and times must be the next one. Okay, nice. Nice. See how our stream's doing. Okay. As the number of entries in a hash table increases, the number of collisions increases. Yeah, that's reasonable to say. Recursive programs are efficient. Not in general. The worst case complexity for a quicksort is O of n squared. Yeah, that's true. Wait, there's no for answer here. I'll just go off what they said here. Okay, so that's good. The Fortran implementation does not permit recursion. It doesn't? I didn't know that. Although these are from really old tests. I don't know the answer to this. I'm just going to pick a random answer. Okay, just happened to get it right. The recurrence relation that arises with the complexity of binary search. So binary search is one instance of T of n over 2. Yeah, so it's one instance of T of n over 2, so it's not B here. And it should be a constant amount of work. Because to find the middle point to split into two pieces takes no time at all. So it should be A. Okay, good. 65. God, I'm getting a lot of emails all at once. Hold on just a sec. Which of the following algorithm is used in the quicksort? We've done this already. That's divide and conquer. Which of the following cases is it possible to obtain different results for call by reference and call by name parameter passing? Passing a constant value, no, because there's no reference for that. Passing an array element as a parameter. Passing an array following statements is true? What does that even mean? I don't even know what that means. Passing the address of an array is a... Oh, okay. Yeah, it should be the address, because if you call by name, that should give you just the number address and not the actual address of the array. So it should be this one. Because these ones are passing the actual elements themselves. Which of the following statements is false? Optimal binary search tree construction can be performed efficiently using dynamic programming. I don't think how dynamic programming can help here. Breadth first search cannot be used to find converted components of the graph. I think that means connected. Yeah, it doesn't. For connected components. Given... Oh, no, it could. It could. Yeah, which one's false? B is false, because you can restart at a vertex that wasn't selected. Yeah, so that's false. Okay. Consider the following two functions. G1 is n cubed for some amount of time, n squared for 10,000 and on. G2 is n and n cubed. So where n is small, that doesn't matter. It's only when n grows does it matter. So G1 is basically n squared for its lifetime, and G2 is basically n cubed for its lifetime. So G2 is the bigger boy. So that means that G1 is big O of G2, that's true. G1 is big O of, I guess that means n cubed. Then yeah, that's right. G2 is not big O of G1. G2 is not big O of n. So it must be A and B. Okay. For parameters A and B, both of which are t of n to the 1/8 a plus 1, and t of b is 1. So let's see. A and B, where it says omega 1 here, that means that they grow faster than a constant, but we don't know necessarily. So at point B, it just hits 1. So it's got to be log base A of something. So log base B of n is equal to some number of applications of dividing by a in the exponent. So log base B of n should be a to the k. So that should be log base A of log base B of n. But that's on a recent test. Huh. Cool. Let G be a weighted undirected graph and T a minimum spanning tree. Suppose we added a new weighted edge. The worst case time complexity of recomputing everything is, so we're trying to add a new edge into this. Of determining if T is still an MST, okay. Oh, so that's just checking if there is a cycle of smaller weight added. So if this edge participates in a cycle, okay, which means that we just need to pass through all the vertices. So this one, I think. Yeah, it's this one. Oh, this one already has the answer. Okay. The root directory of a disk should be placed. Oh, this is a really old question. Fixed address, no, because that can change. Fixed location, maybe. Anywhere, that might be troublesome. A fixed location on the system disk. It's the root directory, so I don't think that has to do with the system disk. Anywhere, no. So I'm going to guess B. Okay. Consider a simple connected graph. Which of the following statements are true? It has n edges, so it does have cycles, so it can't be A. The graph obtained by removing any edge is not connected. That is not true. It's already connected, and it has a cycle. Oh, no. It could be really connected in one piece, and then, yeah. So it could be not connected. Or it could be connected. G is at least one cycle, yep. The graph obtained by removing any two edges from G is not connected. That's true. Because if you remove one, you're at most n minus 1. And if you remove one more, it can't be a spanning tree anymore. So it must be C and D. Oh, this one's easy. So this should be n squared, I think. Oh, no, it has a big O notation. Okay. So it is order n squared, and n cubed is not order n. It is 3n cubed squared, although the 3 shouldn't be in there. The 1.5 shouldn't be there, so I think it should be this one. Yes. Okay, so that one's question with an answer already. The following algorithms can be used to sort n integers in the range in big O n time. None of these can do linear time at all, and radix sort is, I guess, the only one, because you know the size of the integers. Okay, so then none of these I can do or want to do. Choose the correct alternatives and write the corresponding letters. Kruskall's algorithm for finding a minimum spanning tree has a time complexity of, okay, I have to think about this. What was it? I know it has a number of edges to deal with. It is m log n. So it should be mn2. So it's b, d, and e. Well, these are old questions. Choose the correct alternatives and write the corresponding. The following sequence of operations is performed on a stack. So we got a stack here. The sequences of values popped out is, so 10, 20, pop 20, so it's A, B, or D. Pop, oh no, sorry. So the first pop gives us only 10 left. Push 10, push 20, so 20, 10, 10 is next. So it should be B. Yeah. Okay, that already gives us the answer. The numbers 1 through n are inserted into a binary search tree in some order. In the resulting tree, the right subtree of the root contains p nodes. That the first number to be inserted in a tree must be oh, because the first node really determines the ordering. Because the right subtree is with the nodes that are bigger, that means that you have to start with n minus p. Yeah, it should be n minus p. Oh, I don't actually. Why does this answer even have this? That's weird. In the depth first traversal of a graph with n vertices, k edges are marked as tree edges. The number of connected components is, so 2 vertices, 1 edge. So it must be n minus k then. Yeah, it must be n minus k, because in the example of 2 vertices and 1 edge, C would give 0, D would give 1. And there's 1 connected component, so it must be D. In the following tables, okay, so we're just doing a matching problem again. Kruskall's is, it was, yes, m log n. So 2 should be matched with A. Bellman-Ford I know is n times m. 3 is B. Oh, so that should be A, I think. Let's just check. Yeah, that should be A. Okay, good. A hash table contains 10 buckets and uses linear probing to resolve collisions. The key values are integers, and the hash function used is just taking the last digit. If these are inserted, in what location would the value 142 be set? Okay, so the first one, 43, is inserted at position 3. 165 is at 5, 62 is at 2. 23 gets a hash collision, so it linearly probes to 4, because that's an open slot. And then 142 gets 2, but 2's taken, 3's taken, 4's taken, 5's taken, so it must be a 6. And that's what we get. Nice. If you guys have any questions, feel free to put them in the chat. In a binary tree, for every node, the difference between the number of nodes in the left and right subtrees is at most 2. If the height of the tree is h, what is the minimum number of nodes in the tree? So what's the minimum? So in the absolute worst case, you would have one node on one side and 3 on the other, or 2 and 4. So the height is 4 in one case, and we have 5 nodes. So it should be, oh no, the height is 3, sorry. So that means it should be, that would give us 4, that would give us 5, 3, and 8, which is too big. So it must be B. Nice. We got this recurrence. I think we've done this one. We did one with like a log n, and it was the same idea, and we got theta n out of it. Yeah, so that's what we got before. Let G be a weighted graph, undirected, and E be an edge with maximum weight. Suppose there is a minimum weight spanning tree in G containing the edge E. So that means there exists a cycle having all edges of max weight? No, that's because you can pick this smaller one. Edge E cannot be contained in the cycle. Is that true? It can be contained in a cycle, but not in the tree. Oh, there exists a cut set, yeah, because you'll be able to cut some vertices from the other ones. And if you couldn't do that, then that means that you can always skip this one edge. But because the minimum weight spanning tree has that edge, it must take it. So it's that one. A binary search tree contains 8 numbers. When the tree is traversed in pre-order and each node is printed out, the sequence of value. Okay, so pre-order is left. Okay. So let's do this. So let's get this up. So let's see. So 5 is some node here. Then 3. So that means that it should be on the left. Oh, no, it's root left, right. I'm sorry. So 5 is at the top, 3 is next, then 1, then 2, so that should be to the right of 1. Then 4, that should be to the right of 3. 6 should be to the right here. 8 should be to the right of this. And 7 should be to the left of 8, and it can't be to the left of 6. So the tree should look like this. So post order is left root right. So that should be 2 first, then 1, then 4, 3, 2, 1, 4, 3, and then it should be 7 next. Yeah. Okay, so that should be D. Sweet. Okay, so let's stop at question 100. So let's do question 100 and then we'll stop. So let G be a directed graph with the set of numbers 1 to 100 if there is an edge from vertex I to vertex J, if and only if either J is equal to I plus 1 or J is equal to 3I. The minimum number of edges in a path from G to vertex 100 is, Okay, so it's like the minimum number of operations either multiplying by 3 or adding 1 to get to 100 from 1. So I can't get there in 4 because if I take 3 to the power of 4, then that just gives me 81. 99 I can do, but it's not the fastest because it's just adding 1 every time. 23? That seems too high. What about 7? Can we do 7? Well, if I go to 81, that's too far. If I go to 10, let's see, 1, I can't, yeah, okay. So if I want to get to like 99 or something. So that 99, 33, 11, 10, because 11 is not divisible by 3, 10, 9, 3, 1. So 1, 3, 9, 10, 11, 33, 99, 100. I counted 1 twice. Okay, so that should be, yeah, that's 7. Sweet. To carry out white box testing of a program, here's the flow chart. For basis path testing of this program, its cyclomatic complexity is, oh, I think it's just the number of paths that can be taken. So 1 for the outside one, 2 on the inside, and there are 2 choices in the center. So I think 3. Nice. An array of integers of size n can be converted into a heap by adjusting the heaps rooted at each internal node of the complete binary tree starting at some node and doing this adjustment up to the root node. The time required to do this is and doing this adjustment. Complete binary tree. N minus 1 over 2, n minus 3 over 2. There are only order n operations. So I'm not sure. I'm just going to say order n. Because there are order n things to do. Okay. We may have to revisit that at some point. Which of the following binary trees has its in-order and pre-order traversals as B, C, A, D? So in order, so let's see. So in order is root left, right. Sorry, left, root, right. So B, root, so it's not A. Left, root. So B does the in order, right? What about the pre-order? So root A, no. So the root for B, the pre-order would be A, C, B, D, which is not the right order. What about this one? So in order is B, C, A, D. So in order, left. So C is wrong, so it must be D. If let f of n, g of n, h of n be functions defined for positive inter, such that f of n is smaller than g of n is not, so g is strictly bigger, and g of n is exactly the same as h, it looks like. So which of the following is false? So the sum of them is big, yeah, so A is true because g of n is big O of h, and f is smaller than g. F of n is big O of h, yeah, because f is smaller than g. F, I'm not sure what that h of n is not big O of f because h is the same as g and g is not f. Then f of n times h of n is not the same thing as big O g of n h of n. Yeah, so that's right. Yeah, it's not the, yeah, it is big O because f is smaller than g. 3 more. We got an undirected graph here using Prim's algorithm to construct a minimum spanning tree starting at node A. Which of the following sequences of edges represents a possible order in which the edges would be added to construct the minimum spanning tree? So let's do the first one. So e.g., well, it says starting at A, which is, okay, so that's not right. So A is not right. AB, no, that's bigger than AD. So it's either, the answer is either B or D. So where do they differ? So then AB is considered. And then this one chooses AC. So answer B chooses AC next, whereas D chooses DF. Those are the same weight. So we carry on. B chooses CF, which is of weight 4. FC chooses weight 4. GE, yeah, B is not right because it chose GE even though it hasn't reached either of those nodes yet. So it must be D. Consider a list of recursive algorithms and a list of recurrence relations here. Okay, so binary search is going to be 4. So the answer is either B or D. Merge sort is two pieces of n over 2 and order n to combine them. So Q is 3. So the answer is B. Nice. And the following paradigm can be used to find the solution of the problem in minimum time. Given a set of non-negative integers and the value k, determine if there's a subset of them summing which are equal to k. Greedy doesn't work. This is just a subset sum problem. Divide and conquer won't work. Branch and bound, maybe. I know dynamic programming works. Sweet. Whew, okay, so I think that is enough for today. So thanks to everyone for sticking around and actually trying to listen to my rambling. So if you want to support the channel, there are many links in the video description where you can do so. You can join our... Oh, I left this on. Oops. Sorry. I left that on by accident. I didn't even see that. Sorry. There are many links in the video description that you can support the channel with. You can join our Discord server, like and subscribe to the channel. It really, really helps us out. There's Patreon and PayPal if you want to contribute that way. There's Facebook and Twitter, all kinds of stuff that you can contribute. So thank you all for sticking around yesterday and today. And I'd like to do this again in the future. So let me know what you think in Discord or somewhere else. And I'll see you next time. Thank you, everyone.